All right, stat students. So we're moving on to the next section here in this unit. We've talked and introduced what a sampling distribution is. We saw my in-class learners use the pennies to create the very first sampling distribution. You also watched the video of the guy explaining what a sampling distribution was. So let's go ahead and check out what we got going on today. All right, so what I'd like you to do in your notes, draw a line, and we're going to be talking about Reese's Pieces candy today. All right, and I would like you to title your notes, what percent of Reese's Pieces are orange? All right, we're going to be using a simulation to do this. All right, we're going to use an applet to create our samples today, so I don't have to have students do the sampling. This is a lot faster. All right, so first I want to define what p hat is. Okay, p hat is the sample proportion. So I think we have written that down once. I just want to make sure that it's clearly stated again for you all. Sample proportion is p hat, and write down this formula here. Okay, so we're going to be using an applet. Let me go ahead and show this, and I'll come back to this so you can write that down. We have a Reese's Pieces candy machine here. All right, and we're going to be taking a sample. Let's actually lower that to a sample of, let's start with 5, just like we did the other day. We're going to take a sample of 5 Reese's Pieces. Now, I'm going to go ahead and tell you that 45% of this machine that we have here is orange. Okay, so we know that going in ahead of time. But what if you were blind to that fact? Could we predict that number using this idea of a sampling distribution? So that's the main goal. So let's go back here. Go ahead in your notes. You're going to write all of this here. Going to so you have this. Let me highlight all this. Okay, so we're going to go ahead and tell you P is equal to 0.45, the population proportion of orange Reese's Pieces, which is essentially the probability that you're going to get an orange piece of candy. Okay, 45%. We're going to take a sample of 5, then we'll go 15, and then 30 Reese's Pieces. We're going to do this exactly like we did with the pennies, and we're going to see what happens. Remember, you'll remember what happened. It shrunk down in size as we increase the sample size. So we want to make sure that that rule keeps happening, that idea that increasing sample size reduces variability, right? All right, and we also want to see if the sample is an unbiased estimator of P. That's going to be our goal. Okay, so let's go to the applet, and let's go ahead and take one sample of 5 candies. So we're going to draw the samples, 1, 2, 3, 4, 5. Okay, so we got 0.6. Well, that's a lot more than 0.45, right? So that's 60%. So our one sample didn't do the job, but remember, we actually had a lot of samples on our other one. I think we had close to 30. So let's do 29 more and see what happens. Okay, so we have this distribution here. Now you'll notice that none of these samples, because this is the sampling distribution here, every dot represents, I take 5 candies and I calculate the proportion, which is this, orange divided by 5, right? The sample size. So none of them are going to actually be on there. Let's do another 30. Okay, and as you notice here, none of them ever get to be 45%, because 45% is impossible for this to actually give you. Okay, so where does it show the statistics? It's supposed to show the mean of this distribution. There it is. Okay, so but you'll notice that the mean of this is 0.453, and that here's the standard deviation, 0.209. So it actually is an unbiased estimator of let me actually do 100 samples. Let's draw those. This one did not have the correct mean. So we're noticing that the distribution is not is not going to work out. The sample size is too small. We're never going to get a 45% sample. So I'm actually going to save this for a comparison. And I'm going to add a new page here, and we're going to paste this in here. And we're going to do a comparison, sort of like what we did with the other. So that's going to stay there. So this is n equals 5 100 samples. Then we're going to do n equals 15, and then we're going to do n equals 30. So let's go ahead and try this again. So we're going to reset, and we're going to take 15 candies instead, and now we're going to draw the samples. And you'll notice that our proportions on the bottom here have already changed. So let's draw these samples. Okay, so 100, and I think the scale is what is the scale here? I think scale is a little bit different, but we'll notice that the mean of this distribution is still a little bit off there. It's still not as accurate as we'd like it to be, and I don't even know if it's possible to get a proportion of 45%. So if I do 10 divided by 15, that's 66%. 8 divided by 15, 53%, 7, 46, and 4. So it's still not possible to actually get a proportion of 45%, which is supposed to be the probability. So it's unlikely that these sample sizes are going to yield results that that give us even a sample that could have our true proportion. Paste this one in. We'll try to line that up. But you can already see that it's a little bit tighter. We didn't have any samples that were 0. It's very unlikely that you're going to get 0 oranges. But it was more likely to get 0 when, you could draw 5. So the odds of getting 5 that are non-orange are more likely. Let's check out n equals 30 and see how that compares. So we'll reset it. We're going to take a sample of 30 candy. So 100 samples of 30 Reese's Pieces. We're counting the number of orange and creating the proportions. Here we go. So it's going to do the work for us here. Okay, and we can see the mean is super close to, mean is very close to getting us to that 45%. And is 45% possible out of 30? Well, I know that 15 is 50%, so let's do right there, so 13. Well, see, still not possible for this sample size, for 30, okay? But you can see that it is getting better. And you'll also notice that the standard deviation is decreasing. All right, it is becoming less and less spread out. Less and less spread out here. All right, and obviously our scale is changing as we are going. But this one is, if you think about the numbers, it's getting squished in every single time if we had the same scale. Okay. But you'll also notice, just look at the standard deviation. It goes from 0.225 to 0.128 to 0.086. So now I want to actually try this with I want to try this with n equals, well, actually, we'll do it up here. I want to try this with n equals 100. So 100 samples of size 100, and we know for a fact that we can get 45% as a sample of 100 candies. Okay, we know that. So now we're going to draw those samples. 100 samples of size 100, and this should be even smaller standard deviation, which means it's more concise, and that's going to make it less biased, and it's showing the whole animation. Let's see how far. Okay. So there's our sampling distribution of 100. We had some very far outliers here. That's pretty low there. But we're getting even closer to that 0.45. So we're seeing that the larger standard deviation is less variability, and then we talked about that. And the larger the sample size, the less bias that we're having here when we compare these. And again, you can't really tell that it's much less, but that's pretty significant changes in our standard deviations. Most of them are clustered around that 0.45, even though we don't see it on the bottom. Okay. Now you'll also notice one other fact with this. If I keep drawing samples, so I'm going to turn off the animation. Let's do 100 more. All right, and it's going to get closer and closer. Draw another 100, and then another 100, then another 100. All right, and it's just going to get closer and closer, and now it's staying almost exactly on that true proportion that we had talked about, how many are in there. So we're at 700 samples, 800 samples, 900 samples. Keep going. And it's just going to get better and better. Let's do 1,000 samples at a time. And now it's going to be very hard to change that probability. It's almost perfectly locked in at 0.0 or 0.45. You're also noticing something else happening to our sample distribution. I wonder if you're noticing that. What do you see there? As I just keep going up, I'm at 1,200 samples. Let's actually increase this to 10,000 samples at once. And we keep going. 10,000 at a time. You should be saying, wow, that is starting to look like a normal distribution. And if we approximate it to be normal, yeah, look at that. It is approximately normal. That's right. We have approximately a normal distribution. And that is what's going to happen every single time I do this. Like, let me reset it, and we'll do 10,000 at a time. Draw the sample. Even with 10,000 samples, it starts to be normal. Let's do 1,000. And with 1,000, it's pretty close to 100. Let me reset it. 100. Not quite there, but it slowly starts to approach the shape of a normal distribution as you add more and more samples. And this is always going to happen with these distributions. Okay? As long as there's no bias involved, your sampling distributions will turn normal. However, if we're only taking a sample of 5, let's go back and do that. Look what happens with 5. It can never have that shape. That was the first one that we did. Or let's do 2. Possible, right? 0.5 or 1. You're never going to get a distribution that has a shape. 15. So 15 sort of starts taking on that shape. 30 easily takes on that shape. 50. So we see normal distributions are occurring here. So there's definitely some rules going on here, some properties with these proportions that we need to talk about. Okay. So we're going to pause the video, and you're going to write down these. You're going to write down these rules. Okay. So in your notes, you're going to say rules for sampling distributions of sample proportion. All right. So I'll let you write that down real quick. I'll pause it. Okay, so you wrote this down, and we're noticing with these, back to it, that look at the mean here of the sampling distribution. It's always going to end up being the actual probability. Let me reset it. I'll do it 10,000 samples of size 50. And look, it's already in 10,000 samples, it's 0.45 already. Let's do 1,000 samples. Let me reset. Let's do 100 samples. 100 samples is pretty close. 200 samples, closer. Okay. So it's already pretty close when you do 50. Let's do 100 samples. Obviously, the higher the sample size, the more likely that you're going to get the true probabilities. That's sort of the rule. But this rule for sampling distribution, the mean of the sampling distribution of p hat is mu of p hat. So we have this symbol here, mu of p hat. I actually want to write that down. So we have this symbol, mu of p hat, which is basically the mean of the sampling distribution. So this little blue line here, this would be mu of p hat. And we're saying that it's equal to the true population proportion, which is p. And we saw that in the last lesson as well. This is what makes it an unbiased estimator. All right, this is, and we're gonna actually, I want you to write this in your notes, this symbol we need to, after you just wrote the other stuff, but this is the, we wanna name this symbol. This is the mean of the sampling distribution of sample proportions. Okay. So write that down. On your next test, by the way, there will be a section dedicated to naming the symbols. I'm actually going to send out a quizzes practice for that probably later this week. But you have to know how to name all these. If you see the symbol, you know, oh, that means the mean of the sampling distribution of sample proportions. So that's something you'll need to know. And we're noticing that the mean of the sampling distribution of p hat is that blue line is equal to the red line. So that's how we're finding the mean of these sampling distributions. We know that if I just keep sampling and sampling and sampling, eventually 10,000 samples, it will end up being equal to it. Okay, the sampling distribution. So we know if we predict, we're going to make that prediction every single time when we see a sampling distribution. The mean of the sampling distribution should be equal if we sample correctly. Okay, we do a random sample, right? Okay, that's the first rule. Next, we have the standard deviation of the sampling distribution is this formula here, square root p times 1 minus p over n. So this formula here, it says as long as the 10% condition is satisfied. So whenever you're working through problems, in order to calculate, and these are questions on the problem set, by the way, whenever you're working through problems to find the standard deviation, you have to check the 10% condition. You need the sample to be less than 10% of the population. Okay. This formula, by the way, for AP students is on the second page, and it's showing right here for one population, parameters of sampling distribution. Mu of p hat is equal to p, sigma of p hat, and it gives you, it's the same formulas that we just wrote down. Now, dual credit students, you don't have this formula. Okay, it's not on there for you. So this is something that you're going to have to memorize. Okay, it is something that you're going to have to memorize for the test. All right. So let's use this formula in this case. Now, the applet itself said that the standard deviation was 0.050. So let's look at this. First off, is the sample size less than or equal to 1/10 of the population? Okay. So that's the condition that always has to be checked before you calculate standard deviation. Well, what is our sample size? Well, we took 100 candies. All right, is that less than 10% of, well, what's the population size? Do we know the population size? We don't. Okay, we do not know the population size. Honestly, the population size, as far as we're known, is infinity, right? Because they're just going to keep making Reese's Pieces forever. All right, so yes, that requirement is checked. So then let's see if we can get this standard deviation that they got here. All right, it's the average distance from the mean. So we use sigma of p hat, our symbol, is equal to, we have our formula, p times 1 minus p over n. That is the formula we wrote down. Okay, p times 1 minus p over n. So let's do that. So it's going to be p, which is our probability, which we know from up here it's 0.45. So 0.45 times 1 minus 0.45. Then we divide by the sample size. Remember, the sample size is what makes the standard deviation smaller. And we're seeing this here. It is division, right? So if you increase that sample size, it's going to make the standard deviation smaller. So let's grab our calculators. So I'm going to make a square root first, and then inside of there, I'm going to make the fraction. So it's 0.45 times 1 minus 0.45 over 100. All right, so notice that this is pretty close to the estimate that they had. So let's pull this back up. It's pretty much spot on, honestly, this compared to that one. If we round it up, it obviously would be equivalent, okay? So we're seeing that happens. Now, this applet's not using the formula. It's actually taking all the samples and finding the standard deviation using the standard deviation formula. Menu 411 is what we normally do, but there's 10,700 samples in here, okay? So that's how that formula works. And then lastly, we're going to talk about the normality of this. What is it that makes this normal, okay? So let's pull that rule back up, or those rules. So it says, as n increases, the sampling distribution becomes approximately normal. And we saw that, right? And so that's as the sample size increases. Before you perform normal calculations, which is what we're going to be getting to, check the normal condition is satisfied. So we have this formula here, n times p greater than 10. See this. N times p greater than or equal to 10, and n times 1 minus p greater than or equal to 10. So we have to confirm those conditions before it's normal. And I'll explain this a little bit further in a second. So let me paste this in. And then we're going to check these conditions based on what we have. So we know for us, it's n is 100 times 0.45, which is the probability. Is that greater than or equal to 10? And then we also, so both of these have to be true. 100 times 1 minus 0.45 greater than or equal to 10. So both of these have to be greater than or equal to 10. All right, so let's see what we get when we do this. So we're going to do 100 times 0.45. That's 45. So 45. And that is greater than or equal to 10, so we got it. And then we'll do 100 times 1 minus 0.45, which is just 55%, so it's 55. Back over here, and that is 55, which is greater than or equal to 10. Now, what went wrong with when we did this? We went back, let's do samples of size 5. Okay, 10,000 samples of size 5. We're going to draw this. All right, now it's close to being normal, but here's where we're going to have issues. All right, so let's try this again with this formula. With this formula, let's move this over. So now when we try to do this, is 5 times 0.45 greater than or equal to 10? And 5 times 0.45 greater than or equal to 10? All right. I would actually, I just want to be clear that I want you writing both examples of this. Where's my... Go back page. Okay. So write this example. So this is an example of normality. And then this here is an example of non-normal. Okay, because when we do these calculations, we start this first one, we have 5 times 0.45, and we get 2.25, which is not less than 10, or not greater than or equal to 10, sorry. And as soon as one fails, so we'll write this. As soon as one fails, it is not a normal distribution. You don't have to even check the other one. As soon as one of these requirements doesn't work, you have shown that it's not a normal distribution. Okay? Shown here. Those are the main rules that I wanted to introduce today. And when you show that a sampling distribution is normal, you're able to perform normal distributions. So that's one of our objectives, is use normal distribution to calculate probabilities involving a normal population. So let's go ahead and look at an example on our problem set. All right, so we're on number 18 and 19 to start. We're also going to we'll actually do all the way through 21 here. So we're going to do this whole problem. So it says in 2010, a 2010 study of 240 randomly selected residents of a subtropical resort city with 82,000 residents found that 5.4% of them have been exposed to the mosquito-borne virus that causes dengue fever. I don't know if I said that right. Suppose the actual percentage of people in the city who have been exposed to the virus is 3%. Let P equal the proportion of residents who have been exposed in a random sample of 240. Okay? So, for this, we are going to talk about this. So they took one sample. So we need, we're going to start by saying N is going to be equal to 240. Now, with that one sample, they found that 5.4% had been exposed to this illness, okay? Now, that's just one sample. So if they repeated this, okay, over and over again, they took 240, 240, 240, just like we did with the Reese's Pieces. We did like 100 at a time. What would be the mean of that sampling distribution of those sample proportions? Well, here's where we go to our rule. Okay, we go to our rule here. What is the mean of the sampling distribution? Well, it's going to be equal to P. And P is the true population proportion. Well, they told us that was 3%. Okay, as a decimal, that's 0.03. So we get A as our answer for this one. Okay, so it's not B. Even though B is what we'd probably be tempted to put, that's the sample proportion. The mean of the sampling distribution of sample proportions is equal to the true proportion. It should be. Okay. Now, what's the standard deviation? Here's where we have to check that 10% condition right here. Is N less than or equal to 1/10 of N? So N less than or equal to 1/10 of big N. Well, what's big N? Well, big N is the population, and they give that to us right here, big N. All right, so is 240 less than or equal to 1/10 of 82,000? That's what we're trying to show. So I'll grab the calculator. And we're going to do 0.1 times 82,000. That's 8,200. So 80, is that less than 8,200? Of course. Now, this is that independence rule, by the way. That's what the 10% condition is. I think that needs to be written on here. Let me actually draw that. You guys need to add that to your note. This proves independence. So let's write that down. Okay, independence. That's what it's showing. Which means one outcome, if I get one person with this virus, it's not really changing the probability that I get another person with the virus. Okay. All right. So we've satisfied this condition. Now we can actually do the calculation. So we want the standard deviation of sigma of p hat. And remember that formula is p times 1 minus p over n. So that's going to be, we have 0.03 times 1 minus 0.03 over 240. Let's, and I need to That up a little bit so y'all can see it. So let's do that one. Make a square root, make a fraction, 0.03 times 1 minus 0.03 over 240. There's our standard deviation. And you can see that it's going to be C on this one. So that's going to be that next step. Okay, that's the first two. And if you're on your next test, there will be questions that just ask this right here, where you have to find the mean of the sampling distribution and the standard deviation. So the mean is always pretty straightforward. It's equal to the population proportion, always. But we have to make sure we identify this as p hat here, okay? We have to make sure that we identify those. The next part, the next two questions on here. So let's look at those. Same scenario. So let's do this. So which of the following conditions had to be met in order for us to use the formula for sigma of p hat? Well, we actually did it, so that's nice. N is less than 1/10 of big N. So it's D, and we did that. That was this one right here. So you can always put that as 0.1. All right, next. If the true proportion is actually 0.03, the probability that p hat is more than 0.54 is closest to. Okay, so here we're using a normal CDF. We haven't done this for several chapters, but now that, and we actually need to we have to show that the normal condition is met. Because look at E, we can't calculate the probability because we haven't satisfied the normal condition. Well, what is our normal condition? Well, this thing right here. Can we show that this is true for this? That's what we want to do. So we're going to do that. So we look at our sample, so it's 240 greater than or times the probability times 0.03 greater than or equal to 10, and is my camera's in the way, sorry, and 240 times 1 minus 0.03 greater than or equal to 10. Okay, so that's what we want to find out, and I'm going to just type this in here to confirm it. So it's 240 times 0.03. So 7 point, so that's 7.2. Is 7.2 greater than 10? It is not. So it fails that one. So that means E is the right choice, which I wanted to get into the normal calculations on this one with you guys. But if it were normal, we could actually do a normal calculation, be menu, probability, distribution, normal CDF, and it's if you remember from our third unit where we have the upper and lower boundary, so it said more than 0.54, so I'd put 0.0549 E99. The mean would be 0.03. Standard deviation would be the one that we calculated, which was that one there. We calculate it, and you'll notice, I think that they're going to have that answer on here. That 0.1456 is D. So if we picked D, that wouldn't be correct because we're not allowed to do the calculation because the sample size, it's not large enough in this case since our probability is so low. Okay, it's not going to give us a normal distribution. Okay. All right, so that's going to conclude this lesson for distributions with proportions. Definitely try number 22 there. Try some of these questions in the problem set. You can check your answers on Delta Math to make sure you've got them correct.